Alright, welcome back. In the previous video, we discussed evaluating limits algebraically, and at this point, we've done the graphical numerical investigation. We've done one-sided limits. We looked limits as they approach infinity. We've done evaluating limits algebraically. We've talked about this idea of our substitution method when a function is continuous. So we're slowly chipping away on what remains. So next up are trigonometric limits. Okay, evaluating limits of trigonometric functions at different values. So in this instance, we have a graphical representation of x times sine of 1 over x. We have 0 times 1 divided by 0. If you watched the previous video, you would know what happens when we have a 1 divided by 0, aside from your instinctive undefined. But what can we do to evaluate this? Okay, and graphically, your intuition should be speaking to you. We're going to not reveal anything. Product law, we cannot do the product law. The reason why we cannot do the product law is because when we take this piece of the function, we get a does not exist. So you might be sitting there wondering, well, what can we do? Well, the good thing is if you are familiar with sine and cosine functions, they're oscillating circular functions, and they're bound, unless you apply scalar multiplication. They're bound between 1 and -1. If you don't believe me, go to the unit circle. Okay? So if they're bound between 1 and -1, we have this compound inequality. Our original function is x times sine divided by 1 over x. Laws of algebra say as long as I apply the same mechanism to all sides of an equation, an inequality, a compound inequality, I'm not necessarily changing the original structure of our function. Now notice, our original function is here, bound between -x and x. So if I wanted to look at the limit as x approaches 0, we can see that it'll be bound between whatever the limits are for these functions. So limit as x approaches 0. Okay. Well, direct substitution here because this is a continuous function, so we know that's going to yield a 0. We know that this is impossible to do in its current form. And we know that will yield a 0. And now take a look, right? If I draw my graph, we have y equals x, and we have y equals -x, thus squeezing our trigonometric function between two more viable functions that we can algebraically manipulate. Which brings us to a very critical theorem. Awkward silence. And that theorem is the squeeze theorem. Assume that x does not equal c, and we have two functions that's a u of x. Two functions that contain our original function, furthermore, and the limit as x approaches c of L of x is equal to the limit as x approaches c of u of x, which equals L. Okay. Thus, we can say, let's use conclude, more academic language. We conclude the limit as x approaches c of f of x exists, and the limit as x approaches c of f of x equals the limit of our bounded functions. Okay. Now, as I said before, this is most commonly going to appear when we have trigonometric limits, simply because of their unusual oscillating behavior. But let's get into some practice. But before we get there, we have to talk about two quick, I like to call them cheat codes, but they are also theorems. Right, so we have important trig limits. The first one being the limit as theta approaches 0 of sine of theta over theta is equal to 1. And the limit as theta approaches 0 of 1 minus cosine theta over theta is also equal to 0. Now, how do we arrive at this? Well, we applied the squeeze theorem. Because we bound this function between cosine theta and one for all values of negative pi over 2 to pi over 2. Okay. So that justifies our first important trig limit. Going to erase this piece to conduct a proof of this one. But actually I'm going to leave this. Okay. Because this begins our exploration here. So since we have this piece of this compound inequality, you can say then the limit as theta approaches 0 of cosine theta is equal to 1, and the limit as theta approaches 0 of 1 is also 1. It's a constant function. Thus, the squeeze theorem yields the limit as theta goes to 0 of sine theta also equals 1. Sorry, that was not for this one. That was for this. Let me clarify. Okay. More common than not, you'll use this more in your career than you will this, but it's also good to know and have in your back pocket. So let's look at one of these in practice, and that will conclude this video. These are very much, trigonometric limits are very much like riding a bike. They are very uncomfortable when you first do them. After you get some more practice under your belt, they become easier. So, okay. in this instance, you should be sitting at your computer and saying, well, there's a little bit of a difference, right? The input of our sine function does not match the denominator. So what are we to do? Well, we do what we've been doing for years. We multiply by 1. And you might be sitting there and saying, well, Joe, how the heck does multiply by 1 help me? It is it's more of a figurative one, because we need to make the denominator match the input. And we can't alter the input, but we can alter the denominator. So if we multiply this function through by 4 divided by 4, which is a 1, we get this 4h in the denominator that is the same as the input. We can, according to our scalar rule, separate the numerator 4 and rewrite our limit as such. This entire thing reduces to 1. Therefore, our limit is equivalent to 4. So, we wanted to, I suppose, summarize what had happened, right? We introduced a 1 such that the denominator became the input, and we applied limit as theta approaches 0 sine of theta over theta equals 1. Like I said before, definitely going to take some practice to get a little more comfortable recognizing, algebraically manipulating, but the essence of the squeeze theorem says that we're taking a left hand and a right hand function, squeezing them. We're entrapping whatever function we're currently given, typically a trigonometric one. Hint, it's usually between -1 and 1. But I didn't tell you that. Because they are oscillating functions that don't go beyond -1 and 1 unless they are being scaled and multiplied, and then manipulating them as such. Alright, I'll see you in the next video.